beautiful posters by Daphne and others on landscape shown those days. So it will be on similar topics. I'm not going to talk about amorphous materials. I'm going to talk about those stuff, iconic images of our times, right? Those are deep networks. And now you can't avoid them. They're extremely fashionable, maybe for some too fashionable, but I think their success is raising quite fundamental questions. So with respect to science, obviously, you have lots of work now that are using AI, using deep learning to analyze their data. I mean, that's this arrow, if you want AI for science. I mean, I would say there is a double arrow, because now as a scientist, you can also chat with ChatGPT to actually go faster on your science. And I don't know if you guys have tried, but in the last month, it became really impressive. I mean, the level of reasoning, you bring a model, and they can solve in 10 minutes things that would take us more time. I mean, so me at least. So I'm curious to know who is actually, using generative model, ChatGPT, to do science. Okay, is it mostly for, because, I mean, if you write programs, it's huge. But even now for doing theory. This ChatGPT is a generative model. Today I will not talk about generative model, it's tomorrow. Today I will talk more about the classical deep learning, like supervised learning, trying to learn to distinguish cats from dogs, for example. But today it's like, it's not AI for science, it's more like physics for AI, right? Can we fight back and try to use physics to think about why this technology works? Because maybe something that most people don't realize is that you have this amazing technology, but so little is understood about it. Well, that's why I think for theorists, it's actually a great field. I will review partly the field, partly our work. Our work is done as a collaboration with many people. The thing I will focus on today, I mean, I should really talk about Mario Geiger, Clément Engler, Arthur Jaco, Stefano Spiegler. All the others too, but those were leading forces in that. And this review will cover most of what I will discuss today. So this slide is maybe the most important. It's really one central reason as to why deep learning should not work, okay? So let's think about what deep learning does. For example, it can make sense of images, okay? Or it can interact with you on text. And the problem of both text and images is that those data, they lie in very large dimension. So for example, for images, if you have a naive estimate of dimension, that would be the number of pixels. An image is a vector, and you have tens of thousands of pixels. So those objects, in general, lie in large dimension. Okay, so for example, an example of task that you would like to do is to, and that's the sort of things we'll be discussing today, is computer vision. Can you classify if this is a dog or a cat? And maybe you're given a large training set. Maybe you have 1 million of pictures, and you know which one are cats and which one are dogs. Okay, those kind of tasks, naively at least, they should be impossible because of something that's called the curse of dimensionality. I don't know if you heard that name, computer science. It's a very well-known concept, and it's something that we all know. As dimension, it's just saying the volume, think about a cube, the volume goes like, the edge of the cube to the power d. It's exponential in the dimension, right? So it means that volume became immense if the dimension is large. So it means that in large dimension, it becomes impossible to nicely sample space. So you will never bring points close to each other. So if you think about it in one dimension, if you have 1 meter and you give me 100 points, in average, they will be separated by 1 centimeter. If you give me 1 meter square, they will be separated by 10 centimeters. If you give me a cube, even more, and so on. But in large dimension, those points, they never get closer. The only way you make them close is to have an exponentially large number of data in the dimension, and it's astronomical. It's just never going to happen. Now, what you can prove mathematically is that if you're trying to do generic tasks, for example, fitting a smooth function, the only way you can do it, whatever the algorithm you use, is by sampling nicely spaced, by having those points get close to each other. So it means that generic tasks for generic data are actually impossible to achieve whatever algorithm, whatever brain you use. So the fact that those algorithms can distinguish those two guys, or that your brain can do it, means that those data are highly structured. And so what in the structure of data make them learnable is one of the fundamental questions of machine learning, which is not well answered currently. I will discuss this question more next time, but it's key to have it in mind.
Can I have a question?
So, sure.
When you speak about P points, and you say it must be highly structured, you mean that highly structured, you mean that they need to be somehow close in space? Is that what you mean?
Okay, very good point. So there are two ways you could be structured. Say you're trying to learn a function. It could be that the distribution of data is highly structured, like how are these points localized in space? Or it could be that, the function you're trying to learn, the task, is highly structured. So for example, if you're trying to learn a function f of x, it could be that x has the distribution of x has some structure, or it could be that f has lots of structure. And the two are really important. So very good question, Karin. Thanks. Yes. Okay, but we actually know that it's possible to do that. And we know that a key aspect of this mystery lies in those algorithms. They can do jobs that were believed to be impossible before. That's, for example, deciding what's on an image or playing Go. Go is also highly dimensional. The number of configuration of Go is larger, than the number of atoms in the universe. So how do you learn a machine to play Go? Because you never see twice the same configuration. You use deep learning. So how does that work? So essentially, deep learning algorithms, I will tell you a bit more what they are. So those guys are neurons, and those edges are weights. So essentially, the number of parameters is the number of edges, the number of edges on this image. And it's just a fitting procedure. It's a function that takes as input your data. This function, therefore, depends on the data and on the parameters. So this is a dependence on the data. xi is the data I, let's say this guy. W in this notation is the vector of parameters. So xi is in large dimension, W is also in large dimension. You can have billions of parameters. And what you do, for example, for classification, is that every time you have a training set, right? You have supervised examples. I mean, so you have examples where you know what they are. And every time in your training set you have a cat, you will ask the weight to evolve so that, say, this function is larger than some number that we call the margin m. Okay, think currently m equal 1, but later in the talk I change m. So please place m in your brain. It's a margin. So if the margin is 2, you want this function to be at least plus 2 if it's a cat. If it's a dog, you want this function to be smaller than minus 2. Okay? That's just a fitting procedure. Fitting is fine, and I will talk about fitting quite a bit today. But what you really care about is prediction. Prediction on new data that you've not seen before. So actually, one way to test performance, predictive power, it's also called generalization performance, is if you give me, so now you give me a new picture that was not in the training set, and as a predictor, you will take the sign of this output. You'd say, if this is positive, it should be a cat. If it's negative, it should be a dog. And you look the probability where you make mistakes. This is a tester, okay? you want this number to be as small as possible. Yeah? That's the general framework. Are there any questions on that? Already. So can you shift the images? So that's an excellent question. I think the question is, it's a hotly debated question in the field, which is out of distribution generalization, which is the game I will be playing today is you assume some distribution of the data, you take some finite amount of data from it, and then when you test, you take new images from the same distribution. And I think you're asking me, oh, but what if you're changing the distribution? And that's...
Wherever it is, it could be in a corner, it could be in the center, whatever. You focus on a particular region of the whole image, and you don't pay attention to the rest. So I wonder how you do that with this, where every pixel is a sort of equivalent.
So let me, to phrase the question very generally, there is a big question in the field, which is if the data has some probability and then you shift it. For example, you learn to add numbers, you ask ChatGPT to add numbers which are 2 by 2. And then suddenly you ask a 3 by 3. This is called out of distribution generalization. Big question. For those sort of architecture, typically what's used are CNNs, and they build in translation invariants. So simple symmetries can be built in. And it helps to reduce the number of data you need. Yes?
Even without CNNs, I mean, sufficiently large, even just MLPs can, at least in theory, still learn those sorts of symmetries anyway, though, yes?
It will learn the symmetries if you are in distribution. But if you're out distribution, in an MLP, if the cat was always there, but then you show a cat there, no, it's not going to work. Because MLP, they don't translation invariant, so they've never seen anything on those pixels. Weights on those pixels would just never be learned. Other questions? MLP are multi-layer perception, sorry. There are some experts in the field and others. Okay, questions? All right. Okay, cool, but it works, but the principles to understand why it works are lacking. And for example, the fact that we don't really understand this curse of dimensionality business means that we really have no clue as to how many data we need to learn a task. So maybe it's like over the 10 power 5, the number of data we need. But why isn't it 100 or 1 billion billion? Okay, we don't really understand those questions. This slide. Okay, this slide is just interesting because it's also there are several ways of physicists getting interested in machine learning. In the 80s, John Hopkins got the Nobel Prize for it and so on. Then it died out and it came back. And now recently, AlphaGo triggered a lot of us. We are Go players. ChatGPT is bringing now a lot of string theorists and others into the game. But attraction also came from notions that simple empirical laws appear to emerge. And for example, for ChatGPT, so I'm not going to detail it, but the way you train ChatGPT is you hide actually words and you ask a machine to fill up the gap. What was there? Okay. And you can look at some measure of performance, how good are you at filling up the gap, as a function of number of parameters. And clearly, this will also depend on the number of data on which you train. And what people observed are scaling laws, like things appear to scale. Performance and number of parameters appear to scale. Performance and number of data appear to scale. So that's something we and others are working on a lot. Today, you will not hear so much about it, but in general, one question we'll be discussing is, hey, how many parameters do you need and how does it matter? So what you see on those curves is that it's better if you increase the number of parameters, but if you have a limited number of data, at some point this saturates. It's not giving you additional performance to add the number of parameters. Okay, there is something beautiful about deep nets, is that they build what's called interesting representation of the data. I will tell you in the next slide also mathematically what's the operation that's done to go from one layer to another. You iterate this operation. But what I want to point out is that after the fact, after training, you can ask, what do those neurons respond to? These neurons, you can look at the output, but you can also look at neurons, and they have learned to respond in a specific way to the input. And if you look at neurons that are close to the input, what you find for images is that they learn to respond to low-level features of images, like edges. Is there an edge somewhere in the image here? So you could ask me, how do you know that? Okay, I will tell you the story for this guy. Okay, so if you go deeper and you look at closer to the output, you start to have neurons that respond to much more abstract aspect of the data, like having a human face. And does this face has eyewear or not? And this is for a cat. It's beautiful, and your brain works more or less like that. Actually, it's an entire field of connecting what CNNs and or visual cortex is doing. There are lots of similarities. There is also this hierarchical representation of the data which is emerging. Maybe just to, how do we have this sort of interpretation of what's going on? What you can do is you look at one neuron and you ask, how do I optimize the input such that this neuron responds in the strongest manner? And that's how you get those kind of images. Okay? Again, that's a beautiful question. There would be much more to say than what I will be discussing in this talk, but in this presentation, if I have time, I will still discuss this question. Is it always the case that deep nets learn interesting representation of the data or not? And we'll see that there are different regimes. And in some they do, in some they don't, and they still have performance. Do they perform less well or as well, or what's going on? Okay, so finally, so this is a setup. This is mathematically defining what the deep net is doing, and that's a multi-layer perceptron. It's not a CNN, but for this, for what I'm going to say today, it doesn't really matter the difference. In red, you have the symbol you should remember. So one important aspect is the size of your training set, P. Okay, so the number of pictures, let's say 1 million. And each training data comes with an image, this vector of pixels if you want, and also a binary label, let's say if you do binary classification, +1 for a dog, -1 for a cat. Okay, so another, just like P, there is another one that's going to be super important, is the number of degrees of freedom of the machine, the number of parameters of the machine. And this will be N, okay? N is related to the width. So think about a sort of rectangular architecture to make it simple. So the width is a number of, we call those guys hidden neurons. So here it's 5, so here H is 5, okay? The number of hidden neurons. And there is something like the depth, the number of hidden neurons. For example, here L is 3. You have 3 layers of hidden neurons. So essentially the number of parameters is, if it's a fully connected, if every neuron talks to every other neuron in the next layer, the number of parameters goes like H squared times L, okay? So in this talk, we will be worrying about, or interested in the limit where the number of parameters goes to infinity. And what I will be discussing in this talk, other limits are interesting, but we can't cover everything, is the case where the width, the number of hidden neurons goes to infinity, okay? Okay, so now finally, I will tell you how we define mathematically the output. It's defined iteratively. This is the activity of some neuron beta. So, and they are all doing the same thing, except with different parameters. So it's essentially, one neuron will make a ponderated sum of what the neurons in the previous layer are doing. So this is your ponderated sum with parameters that are, in that case, specific to these neurons, okay? It makes a ponderated sum of the activity of the previous neurons. it can add a bias, which is a single parameter here, and it acts on this term with a nonlinear function. And typically what's used is a linear rectifier ReLU, which is 0, and then boom, like this. It's very important to have nonlinearity, because if you didn't have that, the only thing, a product of linear operation is still a linear operation, and at the end you could only create functions that are linear in X, which would be quite boring. In fact, there is a theorem that I will not cover that shows that in a neural network, even with a single hidden layer, if it's wide enough, okay, it could be immensely wide, you can represent essentially any function, any continuous functions. So you have this representation theorem, but you need nonlinearity to do that. And this, I mean, certain type of polynomial would not work. You could only make polynomials. This is good. Any question on the mathematical definition of a neural network?
I have a question. Thing like this, it seems to me that there is no huge difference between L and H. You mean, so of course it does, but
in terms of number of parameters, no.
Okay.
And for what I'm going to tell you today, I mean, I'm going to fix L and take H to infinity. But maybe if you ask this question next lecture, okay. I will be able to, yeah. Okay. Okay, so now how do you actually train? And that's where there is this business of landscape coming in. You build a function which is large if you don't fit well the data. It's small if you fit well the data, and you will essentially do a gradient descent, do a minimization of this function. You will change a parameter so as to fit better the data. Okay, so this, it's called the loss function, but really you can think of it as an energy function. It's a sum on all data of a quantity that tells you if you fit this data well. And there are many choices of this little function L. For binary classification, fitting the data well only depends on the product of yi times f of xi. So in my game, you want f to have the sign of yi. So for example, what you can do is, if it doesn't have the sign, this quantity is large, you're not happy. And you have a margin. You start to be happy when this quantity is larger than m. Okay? That's one example. People also look cross entropy and things like that. There is, and many of the things that I'm going to discuss, doesn't really matter, the loss you choose. In practice, this is called the hinge loss. It performs on, say, on images and so on, very similarly to cross entropy, which is often more used. One aspect that we like with this loss are two aspects. One is conceptual, that this problem then becomes a satisfiability problem. Because if you want to bring this loss to 0, it's a sum of positive terms. Each term has to be 0. And for a term to be 0, it just means that you have this sort of constraint, which is a nonlinear constraint on the W, because the function is not linear in the parameters. So it's nice. I will talk about satisfiability. Another way is that I think what's good for physicists doing this, going to the theory of AI, is that you can, a key aspect that you can do your theory and you can test them with your computer. You can actually do experiments. And that's something we like to do much more than mathematicians, even computer scientists. We want to have a theorem, but we accept to go in the jungle and to test ideas and sometimes observe new things. And the good thing about this loss is that if you are in the satisfiability region, at some point, you do a gradient descent. At some point, this loss will go to 0, and the dynamic would stop. Other losses have some exponential tail, like cross entropy, and then, truly speaking, it will never stop. So you'd have to have an arbitrary threshold, which is when do you stop? So we like not to have that, but we also do both. I mean, everyone, yeah, following? Okay. Okay, so then how do you learn? Well, so the thing is, you initialize your parameters randomly. It's going to play some important role. You initialize them randomly with some distribution. And then, essentially, you do gradient descent. Sometimes some stochastic version of it. But in today's lecture, I will not discuss the distinction. So think about just flowing down this landscape. Problem is, it's a complex system. I mean, this landscape is highly dimensional. You can have billions of parameters. And there is really no reason why it should be convex. So you could really be stuck in local minima. And Jan, if you talk to Jan LeCun and others, the grandfather of AI, they really complained that they were abandoned after the 80s because mathematicians and computer scientists were saying, wow, we have no proof that your algorithms are going to work because it should get stuck, there is no convexity. Let's do something else, like kernel methods that you will hear about. And they pushed, and at the end, it worked better than other methods, and now everything is, so we should sometimes not listen too much to theories. And that's it. So, but that was a big worry. So that's raising the question of why aren't we stuck in bad local minima? What is the geometry of this landscape? Okay, and there have been quite a bit of studies in that, and something we got particularly interested in, and I will be discussing, is if you do classification, what is this landscape, and does it have a phase transition for a certain number of parameters? And okay, it does. It does, and and I'm just going to connect it to physics. There is a very direct connection between this problem I told you about and a well-known problem in physics, which is called the jamming transition. Who has heard about the jamming transition here, just to have a sense? Okay. The jamming transition is also about a problem of satisfiability of constraint. Some of you may have heard of KSAT, where you have discrete spins and you need to satisfy constraint. But here, the physics is slightly different because your degrees of freedom are continuous, just like in deep learning. So this is it. You have, think about that as elastic particles, and they have a finite range interaction. They want to be pushed apart. Just like Jasna's emulsion. That would be a nice example. I don't know if Jasna talked about it. So if you are at small packing fraction, you will manage to bring your energy to zero. You will hit the ground. But if you are at large, there is a threshold where you don't, and you have a glassy landscape, and you get stuck in a local minimum of the energy. And you have a very large number of those, in fact. Okay. One of our organizers is a specialist on that, and actually you have some poster on that question that's related to that. We had a 3-minute talk about that, actually, which is, can we think about this problem in terms of counting constraints? I told you constraints have to do with pairs of particles. They want to be pushed apart. And there are certain constraints that are not satisfied, those guys that overlap. Let's call it n delta, the number of particles in contact. You could ask, when I start forming solids, how does this number of constraints compare to the number of degrees of freedom, n, which would be the number of particles times the dimension of space? And for spheres, maybe it seems obvious, when it jams, when it just starts jamming, those two numbers are equal. You just have enough constraint to forbid motion. Boom, it becomes a solid. But maybe more surprisingly, if you are ellipses, it's not true. When you just start to form a jam system, the number of contacts that you have is smaller than the number of degrees of freedom. You have a system that's under constraint, and still it's solid. Isn't it strange? Why am I telling you all of that to you guys? Why are we doing mechanics? Because this means essentially that those continuous satisfiability problems have several universality classes. And one is that you can jam like spheres, and one is like you can jam like ellipses. And it means that these landscapes are going to be quite different in the two cases. So in both cases, if you look at the energy as a function of density, it's 0 when you can satisfy the constraints, and it grows up. But this is very different. That's the number of unsatisfied constraints and delta over the number of degrees of freedom. I told you for spheres it was 0, and then boom, it goes to 1, and then grows. But for ellipses, it goes to something smaller than 1 and grows. Because of that, the geometry of the landscape is actually very different. So you can look at the curvature. Maybe you guys know that in high dimensions, the curvature, you have many directions for the curvature, and it's all contained in what's called the Hessian matrix. You just diagonalize it, gives you the set of curvatures of your problem. The Hessian matrix is related to the vibrational modes in elasticity, okay? So you look at this curvature of the landscape, and what you have is that at jamming for spheres, this density, okay, so I'm looking at vibrational mode. So it would be really the square root of the eigenvalue of the Hessian. So this is really, if you vibrate at a frequency W, the system, what is the number of vibrational modes that have this frequency? And it's flat at threshold. And then if you compress further, you will erode it. But for ellipses, it's very different. You have at the threshold, at the jamming transition, you have a delta peak, then you have a gap, and then you have a continuous distribution. I should give some names. Many people, I mean, it's a field of people. Many people looked at those ellipses. Alex Donev, Paul Shaikin, Torquato. I mean, I'm going to give you an explanation for why there is a difference. They got that. To compute the scaling and make a scaling theory of all that, Carolina, but I should also give the name of Ikeda, who contributed a lot, Francesco Zamponi, Urbani, and I was also on this paper, actually worked that out. But here I want to tell you why there is such a difference here. And actually there is a simple geometrical explanation. There is a linear relationship between a displacement field, so think about the displacement field of your particles, and, okay, so this guy is a displacement field, it's of dimension n, the number of degrees of freedom, and how you change the distance between particles that were in contact, okay? This is of dimension n delta, okay? You can always say I mean, one is a function of the other, you can always linearize it, obviously, and that defines the matrix, n by n delta matrix. So if the number of constraints is smaller than the number of degrees of freedom, then you find that you have a non-vanishing kernel. You have many displacement fields that don't change the distance between particles. They are called floppy modes. At the linear level, you can move along them without changing the distance. So at the linear level, both of those guys have floppy modes. But the key thing is to look at the nonlinear level. What happens to floppy modes if you go in those directions? And for spheres, you find that you're doomed. If you start to go along a floppy mode, it's become even more floppy in a nonlinear way. Just for a simple fact that floppy modes, the only thing they do is that they move particles orthogonal to each other. And at second order, if two spheres move like that, they will open up a gap. So the constraint is even gone. So if you have a floppy mode, you would be doomed, and that's because you don't have floppy modes in the sphere packing. That's why you need to have a number of constraints equal to the number of degrees of freedom. For the expert, it's called isostatic. This other scenario, which is called hypostatic, emerges because those two guys, for example, a floppy mode those two ellipses could rotate them. At first order, that would not change how much they overlap. But at second order, the nonlinear term, if you think about in your brain rotating those two ellipses, they will start to overlap. So if nonlinear terms can stabilize floppy modes, they will, and you will form a solid which is under constraint. Okay. Questions?
Can you just explain why this density of states disappears and then reappears?
In the ellipsoid case?
Can you repeat the question?
Can you explain why the density of states disappears and then reappears?
Yes, there is some kind of level repulsion. I mean, if you have a delta function of modes that appear here, it's going to spontaneously create a gap. You can think of it as some of those guys here contribute to this delta function. And so it's essentially those guys, they have to be orthogonal to all those, and those additional constraints in the calculation will imply that they have a finite frequency. It's a mathematical understanding here. Okay, there will be, that's related to floppy system. Okay, well, I will. Okay, so why am I telling you about all that? Because there is an analogy between deep net and particulate system, just from the fact that both are satisfiability constraints. In one case, for your jamming, those are the position of the particles and their angle if you have ellipses. For deep nets, it's just the parameters, which are called weights. In one case, you minimize an energy. In the other case, you minimize a loss. In one case, the energy consists of pairwise interaction potential. In the other case, they corresponds to individual loss term coming from a single data. And the exact constraint are that, you know, for jamming, particles must sit at a distance which is larger than d. Whereas for the deep net problem is that each data must be satisfied by something larger than the margin. And this analogy was first developed by France and Parisi in a simple neural network that doesn't have just input-output, no hidden neurons, and extended to very shallow network. And there you can use replica theory. But here we've been interested in deep net, where you cannot use the theories. But there what we could use are essentially the sort of arguments we developed for jamming, the sort of geometrical argument we developed. And I'm not going to do the calculation, but it's exactly what I told you about. You can look at floppy modes, and the key question is nonlinear terms. Are they stabilizing or not? And you find that in deep learning, they can be stabilizing. So you must be in the hypostatic universality class. So deep nets must jam in some hypostatic way. With these arguments, you can also, under reasonable assumption, make something that's sort of very reasonable. It is that if you have many more parameters than you have data, you should not be jammed. Okay, as I told you, I'm showing you this slide because you can do experiments in those problems. So for example, Jan LeCun introduced those MNITs. Those are just those 60,000 digits. We cut them into odd and even in this experiment to just have binary classification. So you teach a machine which has depth 4, I believe. You teach it to learn to classify which number are odd or even. And you can make a phase diagram like that. This is the number of data you're trying to fit. There is a maximal value because this training set has 60,000 data, but you can vary it, obviously. And there is a number of parameters of the model. We just vary the width. And you find that, indeed, there is a region where you can satisfy all constraints, fit all your data by the margin, hit bottom. But there is a region where you don't. And now we took the trouble to study the jamming transition. And for example, you can ask, when you enter, if you want the solid phase here, right close to this boundary, how many constraints are not satisfied, divided by the number of degrees of freedom. And this is this quantity here, the ratio. And I told you in the previous slide that this ratio should be 1 if you're isostatic, like spheres, and smaller than 1 if you jam like ellipses. So yes, that was correct. You jam like ellipses. It's actually hypostatic. And if you look at the curvature of a loss function of those deep nets, it has this gap. Okay, so all good. That was about it with respect to fitting and loss landscape geometry. There is a question there. Confused?
Sorry, the gap on the right, the x-axis of that graph is what exactly?
So those are the square root of the Hessian.
Okay, is this or is this not related to double descent then?
You will hear about double descent in what comes next.
Okay.
How do you know what?
How do you know to estimate your delta n over n for the nets?
So n is just, you fix it as a number of parameters.
Yeah, and delta
and
n?
delta
Yeah.
is just the number of data in your training set that are not fitted by the margin. So you just test.
Oh, so you look at where the margin is and you say what hasn't been fitted,
yeah,
and then
just
you
look.
take that ratio to get this number.
Yeah, it's
Okay.
easy to look at, for each data, what is the output and if it satisfies the margin or not.
Okay, thanks.
Okay, we will move to other aspects, but it means that there's actually a sharp transition between a landscape that's easy and a landscape that's glassy. For the rest of the talk, what will mostly matter is that if you have enough fitting parameters, you're not stuck and you can fit your data. This is raising a question, obviously, that will come in 2 slides with how come are you predictive then? Okay, but before that, I will be discussing the rest in this very nice phase diagram that was done with Mario. Essentially, same task as I told you about, M needs data set and so on. So we're changing, it's not changing the number of training samples, so think that it's fixed. You take all the data set of those guys. But for the rest of the talk, I will be discussing 2 things. One is the number of parameters as before, but strangely enough, the margin will play a role too. Remember, the margin is how much you demand that you fit data. So don't try to understand anything on this plot, just the fact that you have 2 axes. Just the fact that you have those 2 axes. The summary of the first part of the talk is that in a phase diagram like that, you have a region where you are glassy, you're stuck in bad minima. And you have a region where you hit bottom. And once you hit bottom, you can even move continuously in region of 0 loss, okay? Just like you could push particles apart if you're unjammed. Okay, so we're all good. We just crank up the number of parameters and we're not glassy anymore. We fit our data. But all of us, obviously, will worry about overfitting, right? All of us know the story Fermi told, that with 5 parameters, you can fit an elephant. So in physics, we hate models which have too many parameters. So what about models that have millions of parameters? Why should we trust them? And this will be the intuition. And if you open a statistic book, you will find that. If you have a model and you change the number of parameters and you have certain data, and you then fit your model and ask what should be the tester, what should be the, after training, the probability that you do a mistake when you try to predict a new data. You expect a sort of U-shaped curve. And this U-shaped curve comes from the fact that if you don't have many parameters, I mean, your model is not rich enough. It's called a big bias. You're not rich enough to fit the truth. So it's actually better to increase the number of parameters. But at some point, you would overfit. And adding the number of fitting parameters should be really bad. So you should be at a sweet spot. And when we did that, we thought, oh, the jamming transition will be the sweet spot. So we studied this question for classification, and then realized that 1 year earlier, this was studied for regression by Andrew Sachs. And after we did that, Belkin and so on studied the same question and called it double descent. So that's the name that stick to it. And the thing is that empirically, you don't find at all a U-shape. And you don't find that jamming is optimal. You find this. That's why it's called double descent. You go down, you go up, you go down. So where we thought it would work best it works worst locally. So at the jamming transition, it's really bad. Okay? So there are two questions I will discuss. One is, why is it that it's so bad at the jamming transition? That's an interesting limit. And there is another interesting limit. It is second descent. And we were extremely puzzled, because I would like you to really understand this question.
Yeah, actually, as many N as you take is better.
Yeah, I'm going there. I'm going there. No, I was going to emphasize this question. So, what it means is that although you're fitting perfectly your data, it's still better to increase the number of fitting parameters. Makes no sense. Thanks. Makes no sense. But then you do observe it, okay? So I'm glad. Who thinks it doesn't make sense? I'm glad. Just that we were puzzled like you, but then you observe it and you have to say, okay, I observe it. What's going on? So I will tell you our explanation with another group on what happens, and this became a big field with lots of exact theorems and so on.
Are you also going to comment why you have a minima in the jamming region?
So it's not a minima in the jamming region, it's locally worst.
No, I mean, inside of the jamming phase, you have a local minimum.
Yeah, so it makes sense that it goes down initially, because if you have two fitting parameters for a compressor, so this makes sense that it goes down. Then I will explain you why it goes up. So then if I tell you that, you would agree that it has a minimum issue. And then I will explain you why it improves here. Okay? Okay, so the argument as to why it's really bad to be at the jamming transition was essentially stated in the context of regression, where it's not really a jamming transition, but something related, by Andrew Sachs and his collaborators. And I will, in the context of jamming and classification, it's a bit different. You have different exponents, so I will take the trouble to really go through the argument. But at a simple level, this is what's happening. So if you are under-parameterized, your model has really a few parameters, you can't fit your data, okay? So if the ground truth was maybe something like that, that would not be so good. What happens right at jamming is that you can fit your data, but you will have immense fluctuation in the predictor. And actually, that's what we measured here. So this is the norm of this is a function, f of the network is a function, and you can define a norm. So for example, you look a bunch of test points, and you measure f of x on those test points. You take the square, it defines a norm. You average on many points, something like that. This is a log scale. So this is saying f, actually, this is the jamming threshold. At the jamming threshold, you see it has increased by like 3 decades a year. And then it decreases again. So right at the jamming threshold, you start to have immense fluctuations. So for jamming, we predict a scaling that we can check in the data, and it's inspired with discussion with Silvio Friends, actually, for results that are for the perceptron. Again, super simple network without hidden neurons. That's one way we need to, okay, so think about the margin. Okay, so let's think about the following question. Imagine I have a given problem with a finite training set P. P is fixed. Imagine I also choose a number of parameters N. It's also fixed. Now I want to ask the question, what happens if I increase the margin? Is there a point where I can't fit the data anymore? Everything else being the same. Turned out it's not a good question, because you can always increase your weights to increase in a stupid way the function. And so it's a yes or no answer, and there is not an interesting value of M that can distinguish that. But what you can do, how much time do we have left? Half an hour, okay. But what you can do is impose, just like they do for the perceptron, for the expert, impose that this function lives on a ball, so it has a given norm. So the function f cannot be 1,000, or it's of order 1, okay? You can impose that, conceptually at least. If you impose that, then then the good, I mean, you can try to. Then the question becomes, what is, let's say that you're going to play this game where this is fixed. What is the value, given you fixed the number of data and the number of parameters, what is, you know, the maximal value of this ratio where you can fit your data? So if M is larger than that, you can't fit it. And that's something that they can compute for the perceptron, and it's some curve. And this curve will hit 0 at the jamming threshold, and then it is some curve that you can always generically linearize. So you can linearize it here. So if you do this linearization, you find that, imagine that I'm just above the jamming threshold, and imagine that you always have the same margin 1, you will still be able to fit your data if you explode this norm. Because essentially you will be reducing the margin by having a predictor that has swollen. And this linearization tells you that how much you should swell should be inversely proportional to the distance to the jamming transition, which you can check, okay? So you expect from this argument that the norm of the predictor explodes, and that's really bad. I should say, for practical purposes, I mean, you could have asked me, well, you showed us those data from slide 4, and I didn't tell you something about those data for ChatGPT or large language model, is that this has completely driven crazy Silicon Valley, because he told them, well, if we're not smart, but we just increase the number of parameters and the number of data, it's going to scale. We're going to do better. And then all those companies started to actually just scale and put huge amount of money into scaling things better, having more parameters and and larger data set. So this has been very influential for practical purposes, but this does not display this double descent. It's actually the same curve. So here I'm showing you the sort of tester as a function of number of parameters, and this is your jamming threshold, and you have this shape. And I should tell you that this peak, it's easy to avoid it, to destroy it. Not this, less so this second descent here. Okay, so this is the same as here, sorry. So those are again those curves that are showing the tester as a function of number of parameters, but you can do it as you change the size of the training set. If you have more training data, it's harder to fit, and so your jamming transition is shifted. So that's what you see here. For more data, you need more parameters. So the location of this jamming transition depends on the number of parameters, but it's not something you need to follow. I don't really want to discuss this, so focus on a single curve. Yes?
There is some active debate about whether or not LLMs are actually formally overparameterized right now in the first place, right?
Yes, that's true because, okay, so I'm being pushed on the question. There are several reasons why you may not have double descent here. And one of the reasons is that the game we've been playing before is that you give me a finite training set, and you're going to learn the same training set again and again, show again those data many times until you train at the best you could. But often in LLM, you have such a large data set that you show the data only once. But that's quite related to the point I'm trying to make. So, because there is one curve that doesn't have this double descent. So focus on one color is just what we did before. You have a finite problem with a finite number of data. You're looking at the performance as measured by the tester, so you'd like it to be as small as possible. You have this jamming peak, which is bad, and you have this double descent. Here you did not observe it. But you can do simple manipulations not to observe it. And okay, what we reported in this paper was a super simple one. It's just a very common one. It's called early stopping. So instead, and in some sense, LLMs, because they don't see the data many times, are in some sense early stop. But this procedure is, instead of training and up to death, you're going to stop at some finite time. I'm not going to enter in the details. Typically, you can try to estimate the test error, and you stop then. But I'm just going to insist on physically what's going on. By phase transition in physics, we know that things can diverge, but also timescale diverge. So if you want to bring your predictor to be of infinitely large, to be giant, it will take some infinite time. So if you just cut your simulation and just don't go to the end of time, that's called early stopping. If you do it in a principled way, this peak is gone.
I have 2 questions.
Okay.
Nowhere up to now you comment about time here. Where time comes in your equations?
It's the first time I commented, because before I was always pushing gradient descent until its death. I was always going to finite time, to a minimizer.
No, but gradient descent, you need a criterion to stop it, right? There is nothing to do with time. I mean, well, it takes time, computer sense.
So just think in terms. That's a bit like if you take a loss like that. Once you're here, you know at some point all your data are satisfied. That's if you're over-parameterized. If you're under-parameterized, you have minima and you start to oscillate along minimum.
But does it mean that you are less strict to say I would be happy with an agreement that is less than, I don't know, it's bigger than I was?
Okay, so let's say it like that. Those curves, you really try to make sure that you found your metastable state. Early stopping method, now you're forcing me to explain what it is. Okay, well, how do you do it? I told you, typically you have a training set. You can measure a training loss, which is how well you fit your data. But you could do something, you could measure, as you train, you could also measure your test loss. You train with some data, but you have some data you don't train on, and you test your model as a function of time with those test data. And then you can detect when performance is optimum, and it can happen at a finite time. This procedure of early stopping, it doesn't matter so much here, but if you're close to jamming, it's super important. But now you have an explanation why. Because jamming is problematic because it explodes the predictor magnitude, but we know in physics to do that takes an infinite time, close to a phase transition. So by stopping early, you completely cut off this phenomenon. Other regularizations and early stopping can do the job. Okay, that's what I wanted to say about that. That was just about getting rid of this peak. So this peak is still interesting in the sense that it's telling you there is a sharp delimitation between an under-parameterized regime and an over-parameterized regime. It causes problem if you do GD until the end, but you can get rid of it. Now I want to tell you about the second descent. Why is it that you improve performance by adding parameters in a regime where you fit things already perfectly? If there are no questions, I go there. Okay, now let's go back to this phase diagram. Remember, number of parameters, inverse of the margin. Sorry to twist your brain. So here the margin is small, here the margin is large. Okay? I told you there is one very interesting aspect of DeepNet is that they build a representation of the data, a hierarchical representation of the data. You could ask, in this phase diagram, is it always true? So I will be mostly focusing on the over-parameterized regime. So I will not, if you look at those performance, it's best to be here. So I will now be focusing to the regime where you have lots of parameters, okay? So forget about jamming, forget about glasses. You have enough parameters, you can fit your data, okay? Then you can train your networks and ask, did they learn interesting representation of the data or not? Okay, you can essentially, in this phase diagram, the way we did it is just to consider how much, what your neurons respond to, how much did it evolve during training. And what you find in a phase diagram like that is that there is, in this part of the phase diagram, I mean, even you don't learn features. So the neurons change in some very tiny way, which is enough to accomplish the task, but it's called lazy training. You move a little bit, but because you have many neurons, you can still manage to change the output. You fit the task, but you didn't learn representation. There is another regime where, yes, what your neurons respond mostly to change immensely. So I will be now focusing on two very interesting results of the literature. One came from EPFL, the other from several groups, including NYU, on what are those limits. We have to think about this limit when n goes to infinity, okay? But, okay, so this is what I'm going to do. I'm going to first tell you a qualitative argument as to why you have this double descent, and then I will focus on those limits and explain what they are, and then I will conclude. Because I think those are things that are very much studied in the literature, and I wanted to tell you about them. Now, I want to give you a simple explanation for this second descent. It's a scaling argument that you can test with scaling laws, actually, which we did. But here you just get the simple argument. What will be key is the result I will discuss later, that as n goes to infinity, what was understood by those authors in different regimes, that deep learning converges to distinct algorithms that are well defined. I will tell you a little bit about those algorithms in the next slides. In this limit, even the notion of parameters in some sense disappear, as you will see, okay? So when n goes to infinity, you converge to well-defined algorithm. Something that was observed by Neil and others, they asked the following question. I told you that, you actually initialize your weights randomly. You could ask, because I initialize randomly, the predictor I get at the end of my gradient descent should depend, in principle, of where I initialize the network, which parameter I chose. And they found that, yes, it's the case, but if n goes to infinity, this dependence is done. I mean, you see less and less of that. Essentially, what we did is a scaling theory of this effect and showed that this was causing, at least in the various cases that we studied empirically, for images, that this was causing this second descent. So what happens essentially is that n goes to infinity, there are algorithms, there is a well-defined limit. But when n is not yet infinity, you have finite size effects. So essentially, your choice of parameters are going to still impact your predictor at the end. It means that you have fluctuations. Initialization leads to fluctuation in your predictor. What we could predict with those guys, the team at EPFL, was that those fluctuations in their limit was going like the number of parameters per -1/4. You will see where it comes from if I have time briefly in the coming slides. But let's assume this is the case. If you have fluctuation, you can show that it's not bad, it's not good for performance. Typically, how it's affecting tester is quadratic in the fluctuation. Because you don't have a perfect predictor. If you add noise, by symmetry, half of the time it helps, half of the time it doesn't. So it's actually at the second order that you have systematic problems. And so you expect that the change of performance should be quadratic in the fluctuations. And so you actually predict that this second descent should asymptote to some plateau value, like 1 over the square root of n. If you're interested, what we do systematically in this paper is to show that those scalings actually hold. But here, for reason of time, I will show you, I think, a cute procedure to show that this is essentially the effect. And the procedure is that if I do a small manipulation, a small change, I can actually get rid of this second descent, essentially, and get this curve instead. So this is, if you don't do the manipulation, now I will tell you about the manipulation where you get that. And the manipulation is extremely simple, is that instead of preparing a single network with its own random initialization, I will prepare, say, 50 networks. I train them on the same data. The only difference is that they are initialized differently. And then I will use as a predictor the mean of those functions, sort of democracy. And obviously, this is killing by a very large amount any fluctuations. And that's when you do that, that you actually find that this second descent is gone, which shows that this second descent really came from the fact that it was a finite size effect, the fact that you had some randomness coming from random initialization. So now this view has been put in firm mathematical footing by actually mathematicians, physicists, and so on, looking at simple one hidden layer network where you can actually analytically compute that. Okay, so now if I have time,
can I ask a question? Now, can you come back to interpretation of the complexity, the landscape? Because it seems to me that, you know, if I look at this curve, which is when an increase, you're getting better and better, I'm trying to understand what happens in terms of the complexity of the landscape.
Well, so here you are all in the satisfiability. So the landscape became super easy. So it's like for jamming, it's like your particles are nicely apart from each other.
But does it mean that you are changing? The landscape is always the same?
Hey,
or are you?
Well, you entered in a region where the landscape became extremely easy.
Okay, but
I mean, you imagine, so you have flat valleys, just like under jamming, you can move your particles around. So here you have so many canyons where you can move the parameters collectively.
So you increase the soft modes. If you measure the density of states, are you increasing the soft modes when you go down?
Yeah, no, so completely. But also, the point I will try to make is that this description in terms of parameters, I don't think it's a good one to think about what's happening there. So you start to have other terminology, other concept to think about what's going on. So here the notion of landscape and glasses becomes a bit irrelevant. And those guys introduce different languages. So that's why I'm just trying to quickly tell you a bit about those languages. So, okay, I have 2 slides to tell you why is it that in this regime, if you have a tiny margin or you have a lot of parameters, this is lazy. Your weights change just a tiny bit, okay? Okay, so F was your predictor. To make the discussion simpler, let's say that you will do the following. You will, as a predictor, take your network, but you remove the network at initialization. It's simpler to argue than you have a network that starts at 0. Then you train that, okay? So imagine that the margin is very small. So you're over there, and you're over-parameterized. All those arguments are only when you are deep in the over-parameterized region. Then it's not too hard to fit your data, but the key point is that if the margin is very tiny, this function needs to change just a very tiny bit to fit your data. Imagine the margin, you ask them to fit them by 10 minus 3 as your margin. Then the function needs to change just by the super tiny bit. And this will mean that your weights are going to change, in an extremely small manner. That's what's called lazy training. It just comes from that. It's a very simple argument. But the point, what's cool with that idea, is that then you can do lots of math because it means that you can actually linearize this quantity in terms of the weights. Your predictor becomes linear in the weights. So you can think about the gradient of your predictor acting on your change of weights, and that's your predictor. And it turned out that there is an entire literature on machine learning if your predictions are linear in the weights. Those are called kernel methods. The key quantity to look at, that's the kernel. I'm not going to explain it much, but more than just saying that at the end, mathematically, everything is contained in this quantity that depends on 2 data, k, x, y, and it's just the product of those gradients. then a lot can be said. In fact, that was kernel method was a method developed before deep learning. So if we're just recovering kernel methods, say, okay, what are we doing? That would be a good question. I can comment on that. I also want to tell you what happens if you fix the margin, but then you take the number of parameters to infinity. Okay? Actually, that's something that was studied already in the 90s, but not training. People just ask this question for propagation. So imagine you put some data in, and imagine you randomly initialize your weights, but you have now a diverging number of hidden neurons. What are the statistical properties of the function f that you generate? It's going to be a random function, but what is it? It turned out it's just a Gaussian field, because you make good use of the central limit theorems. You have to scale the weights properly, so to have an interesting limit. So each weight is initialized as something like 1 over the square root of the width. If you do that, yes, you can use the central limit theorem, and if those activation is of order 1, then those guys will also be of order 1. The pre-activation before you take the non-linearity would be Gaussian because you're summing many terms. Okay, so, and you can even compute the covariance, I mean, all the statistics of those Gaussian fields. But what the team at EPFL had done, Arthur Jacot, Clément Angler, and Gabriel, Frank Gabriel, is to understand that in this limit where h goes to infinity, even when you when you train, you will be in this lazy regime where the weight change very little. So I told you, oh, it's natural if the margin goes to 0, it should happen. But they understand that the same happens if the number of neurons diverges. And I'm not going to do the math, I'm just going to give you the intuition. What happens when you start to have a huge number of neurons is about positive interference. So when you train, all those weights can conspire in the same direction to actually change the output a lot. But when you do that, the weights change in a very tiny amount, and that's not enough to significantly change, in particular, those gradients, neither the pre-activation of those neurons. So it means that those gradients are going to be controlled. They are going to stay the same on training, just like what I told you when the margin was very small. And again, it means that you can linearize the problem. That's why they call it the neural tangent kernel, the notion that those deep nets in this regime, you can just linearize them and all the information is there. So maybe mathematically, I will tell you just a tiny more, which is that gradient descent, after 4 lines of equation, if you write what it means, you can write how if time is the time you take to go down, you can write how your predictor evolves in time. Formally, that's always true. You can always write it as a sum of data or some function that depends on your data set and the data you're considering, the x you're considering. And then there are those loss terms that take place. Everyone knows that forever. I mean, not you in 2 minutes, but if you take 1 hour and you write it, it's what happens. That was not the new result. And everyone knew that, you know, this quantity is formally equal to the sum on all parameters of the gradient of the output with respect to this parameter on those 2 points, training set and the data you're considering. But what I told you, this interference business and so on, means that those gradients, they won't evolve during training. So everyone knew that, but what people didn't know was that this function, actually 2 things. First, when n goes to infinity, this sum will become a sum on a huge number of terms converge. So it converges to a well-defined function. And this function does not evolve in time. So suddenly, the problem becomes much more tractable. Essentially, what we showed to explain this second descent is to show that it's a sort of a bit complex central limit theorem, like this sum is converging to this function. What we showed with them is that this convergence goes as a rate which is n minus 1/4, which gives the fluctuation of the function at the end. Okay, just for you, maybe it's a bit complicated, but what you could remember is that there is a regime, over-parameterized regime, where you can just linearize your network, and what you're doing is very tiny change of weights, and it boils down to a method that was known before. It's called kernel method. Because then a lot can be said mathematically about this sort of dynamics. Now, I would also like to tell you a little bit about another limit, which is called the feature learning limit. And it's best understood, although since then many works have looked at deep nets, but for shallow networks. So how do you learn features when you're over-parameterized? Yeah, you could think, okay, it's a negative result. You're telling me this regime is a bit boring. You're not doing this interesting, learning of representation. Can you take a limit where n goes to infinity and still learn representations? That would be good, because mathematically, it's always nice to have one parameter less. Like, if n is infinity, it's easier to track mathematically. So the answer is yes. You just need to scale the weight differently. At the end, in the previous approach that I discussed here, weights were rescaled by 1/√h. Here, you will just add, at just one location, an additional factor, 1/√h. So this function will be 1/h. It's the only thing that's going to be different. It's just the scale of your predictor as you increase the number of neurons. That's the only difference. But the point is that because you added this term, your function at initialization is going to be super small. And what will happen is that the only way you can fit the margin is by not being lazy and changing your weights a lot. Okay, so there's a very simple trick to force the system to actually not be lazy. I know I have 2 more slides, okay. It's just to tell you that in this limit, there is, again, a beautiful analogy with physics. I told you about the jamming transition. It's not the same analogy. Forget about that. It's again going to be about particles, but not the same. So now the neurons are going to become your particles. Okay, so I told you that in this limit, the output, your predictor, is 1/h times, and that's the usual one hidden layer, This is one neuron. It's a sum on all neurons, and each neuron is looking at all data, okay? That's the usual thing. There is no trick there. But look at this sum. It's 1/h times a sum. You really want to replace it with some integral. So let's do it. You just replace it. Now, what will enter in this integral is the density of neurons. How many neurons do you have which have certain weights? This is the incoming weight from the input, the outgoing weights to the output, but that fully defines the neuron. So now you can start thinking about, instead of looking at parameters, you think about the density of neurons that you have at any parameter set of parameters. And this is just what one neuron for this weight how it will affect the output. And now again, you can write formally what gradient descent, how it will affect this density. And what you find is not surprising for us physicists. I mean, you can work it out. You find that obviously it's a hydrodynamic description of neural networks. So obviously, because of sort of mass conservation of the number of neurons, the change of this density has to be the divergence of something. This flux has to be proportional to the density itself. And then the force can be written as a gradient of some energy. And what you find formally is that this energy depends on the density of neurons and where you are in your space. So what it means that there is a new analogy of neural networks with a set of interacting particles. And this was kindly given to me by Eric, Jasna's husband, and this is who actually worked on that. And this is not really a neural network, but it's just to tell you that when you have many interacting particles in some potential, which is this analogy, it's good to think about the density and not so good to think about the position of each particle. So that's why there's one interesting point, I think, is that in those 2 limits, you change language. So it's less about parameters and landscape. In one case, it becomes about kernel, this function of two data. And in this case, it's about the density of neurons. Or scaling arguments for the second descent also works here for even more trivial reasons, just because the convergence of this sum, its central limit theorem should go like 1 over square root of h, which is our little n power minus 1/4. Okay, I'm just opening questions because there are so many. Yes, you have those two limits. You could ask, how do we understand which sort of data can be learned in each limit and so on. So that would be another talk. I'm happy to take questions on that. What I will just point out is that, let's say you take some models, like good models like a more modern architecture, CNNs that know about translational space or things like that, and you go there in this phase diagram, and you try to learn images, and you look at test error. You want this to be as low as possible along this axis, and you find, sorry if, okay, this is the margin. So you find that if you're in the lazy regime, it's not so good. Your errors are larger. And if you enter the feature regime, your errors get better. Okay, so this is done in a, okay, I can answer a question about that. So, but in general, you find that for modern architecture and data set, it's better to, much better to learn features. And then now a lot of theories and so on can be done on these questions. That has been done, and happy to take questions. In general, another set of questions that is key. I told you about the curse of dimensionality, but then it was gone. I had never talked about data structure. It was all about how you choose your parameters and so on. So in particular, the question I didn't answer is, there is a plateau value here, which is your performance when you're over-parameterized. This depends on the number of data on which you train. How does it depend on that? How does the data structure affect this relationship? How does the architecture affect that? How does the fact that you're in this lazy regime or your learning feature affect that? Lots of questions. I will talk a bit of that, but not so much. So I'm happy to take questions today if there are some on this. Okay, so I will conclude. Should we be afraid of bad minima in the loss landscape? What we found is that this landscape is controlled by a jamming transition. So don't be worried. You just crank up the number of fitting parameters. You will fit your data. You will not get stuck. But should you then be afraid of overfitting? No, in fact, because deep learning converges to well-defined algorithms, even when the number of parameters goes to infinity, and those algorithms perform well. And this phenomenon leads to a curious second descent observation. And it really has to do with finite size effects caused by dependence on the initial condition of your parameters. And then we discussed under which condition deep nets learn interesting features in the data. And it's always true if you don't have many parameters in your model, but when you have many parameters, it's not the case. You don't learn features if the margin is very small, or if you take the number of parameters to infinite with some, okay. Okay, you saw it's a bit, it's a question of how you things scale. Margin, number of parameters, magnitude of initialization. And here is a question I didn't tell you about. How do you beat the curse of dimensionality? Which data structure confer learnability? And I will be talking about data structure next week. I will take questions if there are some.
Questions?
Hi, thank you for the talk. I just wanted to ask, how general are these results? Do apply to even different models like transformers or recurrent networks, or is just for deep learning?
Okay, so, okay, recurrent networks, I never played with those, so I don't really want to, I mean, it's also, because it makes much more sense for time series or things like that. So, but for transformers, okay, so this sort of results, so we looked at them like 6 years ago for CNNs that were like layer 4 and so on. Then OpenAI has those papers where they look at depth 20 and much more modern CNNs. they were interested in scaling already at the time, and they found those double descent, all those things. For transformers, so I think it's related to another question that was asked. That is, I think it should be there, but large language models are often trained online. So it means you see the data only once. And you have a huge number of, I mean, you know, your large language models are trained on the entire internet. So often you just train a single pass, you do a single pass on the data. So here I'm not doing that. I'm taking a training set, it defines some loss function. I really minimize it, so I'm using all the data all the time. They are affecting, each data is affecting the gradient many times. Large language models, often they are trained online, which means you see the data only once, and then it's a version of super early stopping, so I don't expect to have this double descent, but the data I showed you there was a transformer. This is a large language model. So you don't see the double descent, but you see something quite close to what I'm describing.
Any other questions?
Actually, I have one.
Okay, thanks.
You exemplified the discussion based on a binary classification task. Do the conclusions about convergence depend on that fact, or if you have a more complex classification task?
No, so you can, we discussed that in our papers. It's not super fresh in my mind how we do it, but you can play with multi-class classification with hinges. We created that. It's very natural when you have cross-entropy loss to have multiplication, to have multiple class classification. We did it also with hinge. You can write it formally. No, so I don't expect that it will affect centrally what I'm discussing here.
Okay, thanks.
Okay, I think I can ask one quick question that we can discuss later. But for example, in this curve, let's take the green one. And you say, okay, it's getting better and better as n increases. And then just at this point, how important is to go down? I mean, how good is the solution if you stop, I don't know, at n equals to 1,000?
Yeah, so here it's, I'm on spot because I even didn't put the axis.
Yeah, so this is 1 over m, I guess, right?
Let's try to, maybe I did better somewhere else.
I was supposing it's 1 over m.
Okay, so I'm sorry for this one. So maybe here, well, okay. So in practice, I told you the entire field of large language model, you know, increasing by 10 the number of parameters to do better. I mean, that's what they have been done in the last 3 or 4 years. Just, I mean, that's what they are doing. So they care a lot about those axes. Again, as it's clear here, you need to do 2 things. You need to increase the number of parameters and also increase the number of data. But it's central for the industry. It's central. This is this plot. This is done by Kaplan, who was a professor at Johns Hopkins. I'm using his office. And now he's actually the head of, one of the head of Entropic, you know, one of the big, and he went to that by those plots. And he convinced the field that the thing to do was brute force.
Okay, but in practice, if I would put cats and dogs, would I recognize a dog if I use n equals to 1,000?
If you use what? Sorry?
I mean, because if I think about classifications, dogs and cats,
so
in practice,
I mean, you're pushing me to all those questions I avoided, which is, what is this plateau value? Because it's key at the end, which is, and
no, I'm asking a question is it, if I stop at n equals to 1,000, how close I am from classifying a dog and a cat? You know, that's...
Yes, so...
But does numbers matter? How much they matter?
Is it even in the hidden slides after the conclusion? Maybe it's, no. So what you're asking is key, it's called the training curve. So you plot, imagine you're over-parameterized, you plot performance as a function of number of data. And what you find typically there is, again, a Paulo. except if the data are super noisy, then it can plateau. But for typical data that people use, it keeps improving. And we and others have worked a lot on explaining those power laws. And we have models of large language models of text where we can compute, analytical model where we can compute those exponents. So typically, power law response there.
Okay, so let's go to have lunch, and then we came back at 2 p.m.